Okay, so today we're going to talk about the basics of fractions. And to understand the basics of fractions, where we got to start? We got to start with the vocab. My vocab is color-coded, and anywhere on here I use that color, it's what I'm talking about. It's a brain trick, right? Your brain's been learning colors since you were a baby, since you already know them. We're going to use those colors to kind of pull these thoughts out. First two are numerator and denominator. Top number and bottom number, obviously. Numerator denominator. Since we're recording this, I really hope I spelled those right. Also, my colors are wrong. What are you gonna do? So the numerator is the top number and the denominator is the bottom number. So this is gonna sound weird, so bear with me. Just picture a dinner plate, right? The kind that if you drop it, it's definitely gonna shatter into a million pieces. Now hold on to your plate. Now drop it. And it shatters into a million pieces, right? Are those pieces a fraction? Mm-hmm. Fractions are parts of things, right? Yeah. Are those pieces a fraction? Yes. Think about what it takes to make a fraction. Because you can either have one of two things when you're dealing with parts of things. You can have a mess or you can have a fraction. But they do not mesh, ever. They don't ever go together. Ma'am.
I think it's a mess because they're not actually.
Say it loud so that everybody in the world can hear you.
I think it's a mess because not all of them are like the same shape, the same size.
That's correct. When you drop a plate and it just shatters into a bazillion pieces, you've got big pieces, you've got small pieces, you've got dust. You know, you've got little hunks that fell under the cabinet that you're going to step on and go, ah, like a month from now because they're so small the room doesn't get them. That's a mess. She's right. In order to have a fraction, what we need is every single piece needs to be exactly equal to all the other pieces. Division, right? Even groups. So, now, get another plate. No, sorry, put that plate back. Sweep up the other one. Be very careful. We had somebody cut themselves imaginarily first hour. Sweep it up. Throw those pieces away. Put something over the top of it so your parents don't see it in the trash can and get mad. Just kidding, parents. We would never do that, right? Okay, get another plate. Now, when you drop this plate, you're going to have something very strange happen. And it's going to shatter. Don't care how many pieces, that's totally up to you. But when it breaks, it's going to break into exactly, perfectly, evenly sliced, like a pizza, sections. Picture a pizza. Not from Emos. Emos cuts it in squares, right? We're for a picture like Pizza Hut, Domino's, where they slice them into what looks like triangles with a round bottom. Now, drop that plate. Put on your gloves. Again, we had somebody imaginarily cut themselves first hour, so we have to be really careful with these pieces. Pick up, I don't know, a couple pieces. No matter how many. Pick them up. Gauge how many pieces you hold. Can we tell anything about these pieces?
No.
Are they big pieces or small pieces?
Big piece. Medium.
Small, medium, large, extra large, super size? Who knows? I know Gage has 5 pieces in his hand. I don't know what they're pieces of, though. This is my numerator. Numerator is how many pieces you have. But this doesn't mean anything unless we can compare how many pieces this thing actually broke into. Gage, how many pieces did your plate break into? How many?
600.
600? This is the denominator. This is how many pieces it took to make a whole. When he dropped that plate, his pieces are like microscopically thin. They're all perfectly even. It's crazy how that happens. He picks up 5 of them. His pieces are going to be so thin, they're probably like razor sharp. So he's got to be real careful not to cut his gloves, right? Now what can you tell about these pieces? We picked up 5 out of 600. Bam.
They must be very small.
They must be very, very, not even like regular small. They must be so small, he probably had to pick them with like tweezers to keep from breaking them. What if I did that?
That'd be
What if you only had 6 pieces? Big pieces, small pieces?
They'd be kind of big.
Kind of big, bigger, not necessarily like huge, not like halves or anything, but pretty big. Yeah, I mean, more like pizza slices probably, right? How much of the fraction, how many did he pick up?
5.
How much of this fraction did he pick up? Most of, some of, a lot of, very little of? He picked up very, very little, right? Less than 1/100th of. Almost the whole plate, right? So in order to understand a fraction, you have to understand, or you have to have 2 pieces. You have to know what makes up a whole, and then you have to look at what you actually have. That's numerator and denominator. And a numerator without a denominator is confusion. And a denominator without a numerator is some stuff that we don't really have any place for. Speaking of that, look at, all right, put your plate back on the floor, okay? Be careful. Break it. Got your gloves on?
No.
Put them back on. Safety, please. Pick up all those pieces. How many pieces is your plate broken into?
6.
Her plate's broken into 6 pieces. When you picked up all the pieces, how many pieces did you pick up? Everybody looks at me like I'm a crazy person when I ask that question, but the answer is just as easy. When you had it broke into 6 pieces, you picked up all of them. How many did you pick up? 6. 1 as a fraction is the same number top and bottom because she broke her plate into 6 pieces. She picked up all the pieces. How many plates does she have? I agree and I disagree.
What?
How many plates does she have? 1. But is it a whole?
No.
No, I would not put spaghetti on that plate.
What?
Because it's going to fall off. The plate's in 6 pieces.
Oh.
Do we have all the pieces though?
Yeah.
Could we arrange it to look like a whole?
Yeah.
Yeah. Can we glue it together? Sure.
What?
But the important thing here is when we multiply something times 1. Remember that identity property? Doesn't change it? When we need to change our numerator and denominator to get things like equivalent fractions, make things in simplest form, find a common denominator, these are all words you heard last year, right? They disappear from people's brains pretty quickly. So let's talk about them all together and how they're related, because I think that's going to help. When we have 1 and we break it into pieces, if I wanted to change a fraction, but leave it exactly the same at the same time, you think that's possible? Totally. Good. That means you guys are remembering what 4th grade taught you last year, right? So if I wanted to change this fraction, what I have to do is I have to multiply it by 1. Just multiplying it by 1 doesn't actually change it, does it?
No.
What if I did... Now, notice I'm using my dot instead of the x, because we use x as a variable now. So x could be anything. Dots are multiplication. Remember we multiply straight across, correct? 3 times 3 is what?
3. 9.
9. 2 times 3 is what?
6.
6 ninths and 2/3. Are they the same?
Yeah.
No. Do they take up the exact same amount of space?
Yes.
Do they look the same?
No.
When if you lay them out? If I had a diagram, well, let's make a diagram. Here's 2/3. Now I'm going to take every one of these x's and I'm going to make it into 3 more x's because that's, multiplication. I've got 9 x's, and I circle 6 of them. My diagrams are very similar. If I put this on a circle chart, we look exactly the same. If I put this on a fraction box, it look exactly the same. The only difference here, this is cut into more pieces, correct? So are they the same? No. Are they the same?
No.
Yes.
Yeah.
What's the word for that? Equivalent. They mean the same thing, they're just cut into a different number of pieces. So what happens when I take a fraction that's bigger and I just make it into the easiest possible way to understand? Instead of looking at this, what if I just look at this instead? What form is this called? Can I make this any easier? Can I make these numbers and these pieces any smaller? Can I combine it anymore? No, I can't, can I?
No.
So this 2/3, what form is that called? You know? Yeah, simplest form. Simplest form is when we basically reduce a fraction into the easiest possible way to work with it. Now, why would we do that? And I will give you a hint. This is a very lazy answer. So give me a very lazy answer. Yes, ma'am.
Because it's easy.
Because it's easy. Because math class is hard enough and you have to remember enough stuff. Are you going to make mistakes if you're working with bigger numbers? It's more likely. Are you going to, if you set up your math to be as easy as possible, well, let's not even put it as an if. Shouldn't you always set up your math to be as easy as possible?
Yeah.
There's no reason to work extra hard to get the exact same results. So simplest form is something that we use in order to make it as easy as possible. Equivalent fractions are something we use because of common denominators, right? You can't add pieces that don't match, so you have to make your pieces match. Common multiple we'll talk about later. It's not a very good definition, but it's better than the one that I looked up that was 10 times as long. So just similar groups, and we'll talk about that when we talk about common denominators. Unit fractions are just fractions of any denominator and a 1 on top. Mixed numbers are wholes and parts. So let me give you a mixed number. There's a mixed number, right? 2.5. Let me draw this for you. Two circles and a half a circle. With me? This is 2.5. I'm going to show you something equivalent. Cut my circles in half. How many halves do I have? Halves do I have? How many halves do I have? How many?
2.
More than that, right? 1, 2,
Oh.
3, 4,
5, 6.
5. Is that the same thing as 2.5?
Yeah. Yes. Yeah. No.
Literally, just so everybody on YouTube knows, people are going, because they don't really know, but they want to say yes and no at the same time.
Yeah.
Is it the same thing?
Yeah.
Yes. Is it the same thing?
Yeah.
No. What does equivalent mean? Equivalent means it's pretty much the same. It takes up the same amount of space. You can draw it the same way, but is it exactly the same? No, it's not exactly the same. It's represented just a little bit differently. This, when you put too much stuff in the top, like I'm a third grader here, when you have a numerator that's bigger than your denominator, what's that called? Just a hint. A regular fraction with a smaller numerator and a bigger denominator is called a proper fraction.
Mixed number?
It's a mixed number when it's a mix of wholes and parts. This is equivalent, so it's the same, but not exactly the same.
Improper fraction?
Yeah, this is an improper fraction, right? Whenever I see an improper fraction, I picture driving down the highway and seeing those people that have like 2 refrigerators and 3 bed frames and a mattress all like duct taped to the back of their truck, and their truck's riding super low, and you're like, whoa, how is that stuff not falling out? That's improper. It's too much stuff. This is the same. Too much stuff up here is mathematically useful when we get to multiplying and dividing fractions. And just so you know, multiplying and dividing fractions, I could teach you both of those in 5 minutes. Yeah. But only if we understand how this works. Otherwise, it's leaving us short. Because you don't want to try to multiply or divide 2 different sets of pieces by each other. It's real weird real quick. So this is just the same thing in a different form. That word equivalent, also my favorite math symbol, equivalent, wavy equal sign. I don't really know why, I just think it looks neat. The wavy equal sign means it's about the same, not really far off. They mean the same thing at least, right? We covered one as a fraction, we covered parts of a fraction. Let's start talking about models. Modeling a fraction. There are 2 kinds of learners in math class. People that are really good with numbers, and people that think about pieces of things. I I'm not great with numbers. I'm teaching myself every year to be better and better with them, but naturally speaking, I'm not great with numbers. Pieces of things, yeah, I'm pretty good with pieces of things. When I was in school, most teachers taught fractions algorithm way. Numbers only. So I guarantee you, some parents watching this video right now, or some parents that you've heard, we'll take a poll. We'll report it to YouTube. How many of you have heard an adult complain about how much they hate fractions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How many of those people have been doing a fraction worksheet or have been watching their parents help somebody with a fraction worksheet when they were complaining about how much they hate fractions? And almost the exact same number of hands. Your parents and I mostly learned fractions algorithm, which is fine. It's a good thing to learn a fractions algorithm. It's not a good thing to only learn fractions algorithm, right? Because we're using fractions in real life. We're making things, building things, taking things apart, combining things, separating things, right? We're doing actual stuff. So the people who are really good with algorithm, I'm super going to annoy you because I'm going to make you draw it out and do it visually. And people who are good at visual, I'm super going to annoy you because I'm going to make you do the algorithm too. So everybody's going to be equally annoyed with me during fractions, but you'll at least have one of those two ways that almost everybody is either really good with one or really good with the other. So you'll always have a fallback, even when you're annoyed doing the thing that you don't like to do. You'll still have the fallback of whatever the other thing is that you're good at. So let's talk fraction models. Bar model. Good thing because you can do it with any fraction, and yes, that's what your ruler's for. Bad thing, if you don't use a ruler, it's wrong, period. Why? Why do you need to use your ruler, though?
Because it has numbers. So it can be straight.
Yes, because it's either a fraction or a what? It's a fraction or a mess. Squiggly lines don't make for equal groups. Now, do I expect it to be perfect like computer generated? No, not really. But do I expect it to be neat, straight lines? Obviously, use a tool, not just kind of slop some stuff down? Yeah, totally. Up to you. Doesn't really matter. I'm going to 12 inches because then I can separate that into groups of 3, and it's big enough for you to see. Sorry, not groups of 3. 3 lines. Gonna get this guy straightened out. When you're diagramming a fraction or doing a fraction model, the goal is this. By the way, this doesn't need to go in your notes. If you could pass these out to 4 3-year-olds and none of those 3-year-olds would throw a gigantic temper tantrum because they got the smaller piece, you're good. If you can look at it and go, 3-year-old to throw a fit about that because they're getting a smaller piece, not good. Bad thing about the bar model, it takes a lot of time. You have to be super careful with it. How many pieces is this bar model that I drew divided into? How many pieces is the whole thing divided into? We have 3 pieces.
4.
Out of 4 total pieces. So pluses of the bar model, those awkward fractions like 3/7 or 11/16, totally easy, no problem. Well, at least neat. I don't know about easy. Negatives of the bar model, crooked lines make it wrong. And you have to use a ruler, otherwise you've got, wavy squiggles instead of lines. If you don't measure these spaces, like 9 out of 10 people will have a really hard time even getting them close. It's a very rare person who's good enough with distances to just draw those and be right. Just slap those lines in there without measuring. Good? Circle model. Sad face. Textbooks use circle models all the time. Our textbook uses circle models. I need people who are brave enough to be on camera and have me heavily criticize them. Please hold, YouTube. I'm not going to be that mean. I'm not going to yell at you with roast stuff or anything. Okay, I want you guys to be able to catch, because I'm throwing markers to you. What? 3, 4, 5, 6. Draw a circle model of 1/3, and then bring it up so I can grade it. Yeah, if you're doing notes, I definitely want you to draw this in your notes too. You can. That question definitely should be a hint towards what the problem is going to be. All right, come up. Get ready to be famous for 10 seconds. Nope, that one's too small. This one's way bigger. See it? Sorry, wrong. Told you I was going to be mean. Up. Look, that's way different. Not equal. Sorry, you're wrong. Yep, look, that one's way bigger. Sorry, you're wrong. That's pretty close, but this one's a little bit wider, so it's got a little bit more area. Sorry, you're wrong. Oh, look at this one. Too big. Sorry, you're wrong. Now. I like it. It's very neat. It's not thirds, though. But it's very neat representation of 3/4. Now, a computer can do this. Like, one of the original reasons computers were designed is because that's really hard to do by hand, and it takes a bunch of, like, drawing tools and stuff. One of the original reasons computers were designed were to make designs. Yeah, a computer can draw a perfect circle and divide it into thirds because it's what computers were designed to do. But guess what? Doing it on paper or doing it on a whiteboard is ridiculously hard. They're almost always going to be wrong because your spaces aren't going to be even. So is this a good diagram? Sure, if you're a computer. If you're not a computer, even if you've been literally standing up here doing this all day, like I have, when I do my spaces, this one's clearly bigger. So, when drawing, if you're going to use a circle diagram, pick the fraction really well. You can do fourths easily. But is this one close enough? Yeah,